Thank you, Surya Prakash, for arranging this talk. I also thank Sri Madhavan, Sri Bachelal, Sri Lavendra Kumar, OP Arya, and everyone in Block 3 ONGC for inviting me to give this lecture. I have prepared this lecture about the Archimedes Palimpsest, and at the outset, let me tell you that this word palimpsest is something which is a bit difficult to pronounce, and it appears now and then during the course of the talk. So please bear with me if I am not able to pronounce it correctly all the time. So this is an interesting topic which deals with restoration of a lost book, and it goes back to ancient times and comes into modern times where a lot of techniques were used in order to uncover the text. So here there are a lot of multidisciplinary actions which have been taken, and so it was of interest to me to research this topic. In the next slide, I show you what we know about Archimedes. Archimedes was born in the year 287 BC, and the years 287 to 212, this is the period of time in which he lived. The story which we tell children, and which is very famous, is that of Eureka, where he forgot his clothes when he discovered that he could find out for the king the gold crown, whether it was fake or it was really made of gold. He thought it over and realized that he could find out the answer. But more than that, he was also famous for a number of other discoveries or inventions which are related to engineering. So he was actually a physicist, an engineer, a philosopher, and he had lots of things to his credit, and a mathematician. And in fact, this talk will focus on some mathematical aspects of his work. For example, this invention, the claw. So the city of Syracuse used to be invaded a lot by the Romans. So they used to come in their ships. And Syracuse was a relatively small city without a big army. And they succeeded in defending themselves against the Romans for a very long time. Of course, eventually the city was overcome by the Romans. But the situation with defending their boundary walls was very much fortified by these inventions which Archimedes had put up. One of them is this one, the claw. So here you see in this slide a lever that's actually a kind of a cantilever with a chain attached to it. And they used to lower the chain with the help of some weights and try to see that it gets entangled in the bow of the ship, which the Romans were launching to fight against them. And once entangled, they could actually lift up the ship completely and turn it over the other way, and all the people in it would fall out. Today, when I show you this one with the mirror, so it's something which we are all familiar how we concentrate the sun's rays. There are even applications today for solar energy. But at that time, Archimedes had worked it out that if you use a concave mirror, you can actually focus the sun's rays, and these rays can then be made to fall on a ship and make it catch fire. These pictures, by the way, are actually Renaissance period paintings. So the stories of Archimedes were known and handed down from generations. So it's not just in the modern times that we have been talking about Archimedes. It's a very, very long time since people have been enamored by Archimedes' work. Here is another one. It's called the screw. In this one, the water from a lower underground reservoir can be actually brought above ground by turning a screw. This kind of device is actually in use even today for irrigation and other purposes. The famous quotation is known to all of us about, or maybe not so well known to everyone, about Archimedes. That says, "Give me a lever and a place to stand, and I will move the earth." So you see here the lever. Archimedes understood that if you have a very short load arm and a very long lever arm, you get a very high value for the mechanical advantage. And so you can actually design a lever to lift a weight, no matter how big this weight is. You can devise a lever which will be able to take the load. And in fact, the story goes that there was a ship which the king of Syracuse wanted to give as a gift to the Egyptians. And the ship was built. It was a very big ship, the biggest ever built of the time. And they also were, filling up the ship. It was the goods. It was laden with goods ranging from silks and spices and everything, whatever they would like to give as a gift. And so the ship was ready, but when they found that they were unable to launch the ship, they were not able to put it into the sea. They tried with all the forces they had at their disposal, but no one succeeded in putting the ship into the sea. At that stage, when the king consulted Archimedes, who is to work for the king, he replied that it's an easy task, and in fact, we don't need a lot of men. I can do it single handedly. So, as the story goes, he placed a lever under the ship. The painting which you see on the right shows actually a system of pulleys which was also used. So, he had used the lever on one side of the ship to give it a push, or rather to take it a little higher. And then you needed to pull it. And this was done with a system of pulleys. So you see, Archimedes knew everything about the mechanical advantage of levers, pulleys, and many of his inventions were based on this. As far as the lever is concerned, this is a very important device in Archimedes' work, and we shall see that the method of geometrical construction, which is the subject work or the key subject work in the Palimpsest, is actually based on the lever. So we come back to this lever a little later on again in this talk. So let's focus now on the palimpsest itself. So the name of this book is actually the Archimedes Parchment Codex Palimpsest. And to decipher what all the words here, what they mean, first of all, parchment. Parchment is an animal skin akin to paper. So today's paper was of that time a parchment. Parchment is actually much stronger and tougher than plain paper. It is what was the material on which people used to write in the ancient times. The word, and parchment is made from animal skin. The word codex, by the way, that means book. So that's a simple word here. Palimpsest, this word may be new to many of us. It refers to the process by which an old parchment book could be scraped and reused. This was done because the amount of parchment available to people was limited. And so when they felt that there is a book which is no longer required, they would often scrape or, in other words, erase the existing writing which is on the parchment, and then they would write over it to form a new book. So this is what had happened, and such books are called palimpsests. And the process by which the scraping and rebinding of the book is done, this is known as palimpsesting. Now I go to the timeline of this book. The books which Archimedes has written are listed on the square panel on the left. The Method of Mechanical Theorems, this forms the major part of the lost palimpsest, and that is the theme of my present talk today. There's also floating bodies, measurement of the circle. Then there's a book about the sphere and the cylinder, and spiral lines, as well as equilibrium of planes. So these books are also to be found contained within the palimpsest, but the focus today is about the Method of Mechanical Theorems, because this is one book which is not available in any other source. In fact, it was totally lost to the modern world, and it was uncovered only recently. So this is the main focus and the subject of the present talk. So the story starts in 287 BC. So during the period 287 to 212 BC, and the scene is Syracuse. At this time, Archimedes used to write his works on papyrus scrolls. So papyrus scrolls is the medium of writing at that time. When you wanted to document a work, you actually took these scrolls and you wrote on them, and they had to be rolled and unrolled in order to see the text. So this is the methodology by which literature was preserved in that era. In 212, I now go over to Constantinople. So the period which I'm talking about is 212 BC right up to AD 530, that is after the time of Archimedes. And this place, Constantinople, is today called Istanbul. So in modern times, this is Istanbul, located in Turkey. But this palimpsest, which we, at that time, it wasn't yet a palimpsest, it was just a book, or rather it was a scroll. And these papyrus scrolls on which this book, Method of Mechanical Theorems, and other works were written, were located in the library in Constantinople. During the time 530 AD right up to 1959, not 1950, 950 AD, the original was actually lost, but the scroll had already acquired copies, and the copies were made by unknown persons. In 950 AD, around this period, the process of recording books had changed, the technology had changed. People were no longer using scrolls. The new method of doing this was parchment books. So in the library, in the year around about 950 AD in Constantinople, scribes were assigned to copy material to parchment books. So the scrolls no longer existed after that date, or at least if they did, it's not known where they went. But the scribes copied and onto parchment books. Perhaps there was more than one such book placed or prepared, but as of today, only one of them survived, which is the topic of the present lecture. On April 14th, 1229, so in this case we know the exact and precise date, 14th of April 1229, the location is Jerusalem. Jerusalem is a holy city, is the place for Christ, and it is the location of it is near to Constantinople. Here in this location, Jerusalem, there was a monk whose name also is now known, Johannes Myronas. He erased this book and overwrote it and rebound it into a prayer book. So by their reckoning at that time, it was thought that this book is not useful, and he was in search of parchment on which he wanted to prepare a prayer book. So he had got hold of this book, which was looking like it was discarded, and he took the book and changed it from vertical format, that is your portrait format, into a landscape format, cutting the pages in half. He erased the material by scraping, and then rebound it into a prayer book and wrote on the pages the prayers. During the period of 1200 right up to 1840, this book remained here in this Jerusalem monastery, and the original work of Archimedes in Greek was lost. So this book remained as a Greek Orthodox religious study book and a prayer book, and the location of it was in the Jerusalem monastery. The shift now goes over to a period of time where even in 1204, when the Fourth Crusade took place and many books were burned, this book survived. So this book was not destroyed, it survived this Fourth Crusade. But in 1840, the scene shifts to Constantinople monastery again. So this book was taken By now, it was not an Archimedes book. It had become a Greek Orthodox religious study book, and it was brought into a monastery in Constantinople. So the book returns to Constantinople in 1840. There, after another 6 years, that is in 1846, there was a German scholar who happened to be there in the library, and the name of the scholar is Konstantin Tischendorf. And when he was looking at this book, he was surprised to find that there is actually a writing he could discern below the text. That means the prayer text, which was written left to right horizontally. He found vertical writing from up to down on all the pages, but very faint, indicating that this was a palimpsest. That means that the original writing of a book had been erased and the prayer book was constructed out of old parchment. He suspected that the writing below was of great value, and he had a suspicion about the author. So he decided to take a page out of the book. So he tore a page out of the book so that he could actually show it to a friend of his who was a known scholar. So we are told that when he showed it to his friend, they actually recognized together they recognized the work as that of Archimedes and realized the great value of it. However, nothing came of it at that time, and we don't know what happened exactly to what Konstantin Tischendorf did. But we do know that in 1906, that means another 60 years hence, there was a Danish historian whose picture I have put up for you on the right. His name was Johann Ludwig Heiberg, and Johann Ludwig Heiberg was visiting the library in the Church of the Holy Sepulchre in Istanbul, and here he discovered that there was an underlying layer in this book. So he got hold of this book, and while perusing the book, he discovered the underlying layer. He at once recognized it as that of the lost book of Archimedes, and he photographed all the pages. And he began a transcription which he actually published, and this transcription was based just on using a magnifying glass. So obviously he couldn't have done a great job. He did whatever he could, but there remained a lot more which needed transcription. In 1907, the book went missing. In fact, it was stolen. This happened because in 1907, on July 16th, a newspaper item had appeared in the New York Times, which mentioned that there was a big literary find. So the person who stole it might have been under the impression that the book was of great value. However, it began to appear for sale on footpaths, and a forger at this time in 1929 painted some medieval holy portraits in gold leaf on 4 of the pages. Perhaps the forger might not have been aware of the underlying text of Archimedes, and he was trying to enhance the value of this book in order to sell it. In 1930, a French amateur collector by the name of Cyrex traveled to Istanbul, and he purchased this book from a local dealer. Cyrex was probably aware of the underlying text and realized the value of this book. However, the book was not available to the world. He kept it in his house. It was stored for 60 years in Paris. Part of the time it was in a garden area and in a basement area. It could even have been underwater. The result was that it acquired a lot of mold during this period. In 1971, an event of importance took place where a professor of Oxford, Nigel Wilson by name, discovered a torn page inside a book in the Cambridge University library. This page was the one which was earlier torn out from the original codex by the German historian. So This story now unfolds to the next slide. See, 1 years. When a long time has passed, Cyrex's family approached an expert of the auctioneers Christie's in Paris for appraisal. They were interested to have the book auctioned. They probably realized that it's an Archimedes book, and they took it to Christie's, and the appraiser at once recognized it as an ancient lost work of Archimedes, and it's a palimpsest, and he considered its value as somewhere in the range of 800 to 1.2 million dollars. In 1998, on 29th October, the book was sold by Cyrex's daughter. The sale price was, I am told, about $2 million. The buyer was unknown, but we have clues that the buyer could have been the American billionaire Rick Adams. The timeline going up to 1998 up to the present day is that the unknown buyer uh, uh, contacted Walter's Art Museum in Baltimore, Maryland, USA, and they assembled a team of restorers and scholars for cleaning, imaging, and translating. This was still a privately owned book. The Palimpsest was privately owned by the American billionaire, and it was never handed over to the government. The intention, apparently, of the owner was to make public the book, all the research which would be done with the book, and to make available to scholars every aspect of the book, including its initial processing and uncovering the text, all the research which has been done right up to present times has been possible without government help, by all due to the initiative of a private owner. The data today is actually made available and it is free in the public domain. The Walters Art Museum in Maryland, whose picture you see top right, admission here is free, so you can actually go and have a look at the palimpsest in the way it is presented. You can listen to presentations about it. Here you see also below that a picture of Abigail Quant, who is the head of conservation at the Walters Art Museum, and she is the one who contributed in many ways the maximum to to the restoration of this palimpsest, because the initial work was perhaps, in my opinion, the one which involved the hardest work of all. Before I go to the actual conservation work and how the book was recovered, perhaps you may be already anxious to know what the book really contains. So, and that would give you an idea why the book is important. So, this book actually has in it uh, the first part of the one part of the book is about the method of mechanical theorems. As I said earlier on, it also had texts other than this method of mechanical theorems, but those texts of Archimedes are already known and available in other manuscripts. But the method of mechanical theorems was absolutely unavailable in any other form. The only way that we could get it was this palimpsest, and it was the only surviving copy of this method. And this method would have remained unknown if this book was not restored. Now, let's see what the method is really about. It used to be like this at that point of time when Archimedes was working. Archimedes, by the way, was a student of Pythagoras, and he believed in formal proof of all the theorems and propositions which were mostly related to geometry. Today we would call it calculus, but at that time, let's think of it as geometry. So he had a number of formal proofs which he used to do for the propositions which he published, and the proofs were given by what we now call as the method of exhaustion. The method of exhaustion requires that you know the result and you're just trying to establish a proof of it. And this he used to do often by using what today we would call as a method like limits. So, for example, if you want to know the ratio of the circumference to the diameter, that is pi, of a circle, then you can enclose the circle from the outside using a polygon with many sides, and from inside with another polygon. And then as you increase the number of sides of the polygon, you converge to the circumference of the circle. This methodology is called a method of exhaustion. And using this method of exhaustion, he had actually given the proofs of a number of results. But he considered, the question really came as to how he came to those results in the first place before giving the proof. This was never discussed and never explained, because what was required was the formal proof. In fact, Archimedes himself believed that his method is something which is not rigorous. Today we can make it rigorous using calculus, but of course calculus was far away at that time. It was formalized by Newton and Leibniz much later. But at that point, without the possibility of using calculus, he believed that the method which he used was actually not rigorous. He used to get the results. He used to plan on making some so-called experiments. In fact, the experiments involve levers, as we shall see now. So we come back to the lever. And this is an example where physics is used to derive mathematical results. It's a surprising twist, because normally we use mathematics to derive relationships about the physical world, and we establish mathematical theories, and then we test them with experiments in physics. That's how we do physics. But here we find that he would use an experiment. The experiment would be a thought experiment, which he would do in his mind. Maybe perhaps he did it when he was asleep in his dreams, because they are really very nice, beautiful ways that to derive these kind of results. I will explain the precise nature of this method using levers in the next slide. But here on this slide, I am going to tell you about a couple of, or in fact, four propositions which are given, and he has given the proofs of these propositions elsewhere in other books. But the result he first derived in his own way by the non-rigorous method. So the first proposition in the palimpsest is the area of a parabola segment. The area of a parabola segment in modern language is an integral of x squared from 0 to 1. And today it's a high school exercise to establish the value as 1/3. But he could arrive at this result, and he visualized this result using the method of mechanical theorems. He also gave a proof. So on the right, I give you a picture. If you want to know how the proof goes, you'll have to read it up in other documents, where the method of exhaustion is provided to establish a proof how the area of a parabola segment can be computed to the result 1/3. The non-rigorous method, that is the method of mechanical theorems, establishes this result 1/3 without being rigorous. In his opinion, Archimedes' opinion, the method was not rigorous, so that is why he didn't publish it till towards the later part of his life. So this is the reason why this book became obscure and it wasn't available, because it was published much later, and there were no other copies which have survived. However, it's a beautiful method, and I think you might enjoy it. And this is the reason why I'm giving this talk. I really enjoyed this method itself, and it's a really ingenious method of bypassing the requirement of calculus. It actually envisages calculus's results. It makes infinitesimals. It does everything without really involving calculus as we know it today. The other results which he created were volume of a sphere, curvilinear shapes, which result in rational volumes. So you have an intersection of curved surfaces, that means parts of a circle, or rather of a cylinder, and when they intersect, strangely, you can have an answer which doesn't involve pi. So you can actually have shapes which are having boundaries which are curved as part of a circle, and yet the volume doesn't involve pi. So this was something which he discovered. I think it's something quite wonderful. Then there is his method applied to finding out the center of mass of a hemisphere. This was also something of immediate use because he was dealing with projectiles of all sorts of shapes and also domes, other objects which were there, which he used to deal with. So he became interested to find out the center of mass of a uniform density hemisphere, and he could derive this result from his non-rigorous mechanical method, and he could then justify it by his method of exhaustion. So going on to a little bit more about the method, we slide an example. In this example, the brown line is actually a lever. In this lever, you have a fulcrum which I have shown in the form of a triangle, and he balanced this lever out as the cylinder on the right side, which is on towards the right. It is a cylinder whose radius is 2r. The front of the cylinder is located exactly where the fulcrum is. So the center of gravity of the cylinder would be at a distance r to the right of the fulcrum point, and to the left of the lever at a distance of 2r, he suspends two bodies, a cylinder, sorry, not a cylinder, a cone and a sphere. So the cone and the sphere are hanging from the same lever at a point distance 2r to the left, and both the cone as well as the sphere are hung from this point down. And he goes on to demonstrate with these dimensions, that means the height of the cone is 2r, the diameter of the sphere is 2r. Under these conditions, he tries to establish the balance of this lever. He tries to show that this lever will be balanced, it will be in equilibrium. To notice this, let's start with the cylinder. So what we do to prove this is that in this method is that we make slices. So the cylinder is sliced now. This is something which is very familiar to us in these days of calculus. But imagine that he had to do it when calculus was not known. So he has sliced the cylinder. This is shaded in orange, the region here, and I call the thickness of that T. In today's language, it would have been called delta X or delta R. So let's consider the distance from the fulcrum to this orange stripe of the cylinder as X, and the thickness being T. You can now see that this slice of the cylinder has got a radius of 2r. So its area is pi times 2r squared, and the thickness is t. So I multiply that out, and the moment or torque produced, the moment of the force or the torque, needs a multiplication from the distance from the fulcrum to that point, that is x. So the moment of force for the cylinder is pi times 2r squared times x times t. Now let's make exactly the same slice thickness t on both the cylinder and on the sphere at the same time, so that later on when we move this slice from the cylinder from left to right, these slices on the cone and on the sphere will go from top to down. So the distance of the slice on the cone is again from the tip x, and the distance of the slice on the sphere is x from the top of the sphere. So I've written down the expressions for you here, which you can verify. For the cone, you work out the area, and in this case, the torque is obtained by multiplying it as a distance of 2r from the fulcrum point. So what you need is just the volumes of the slices, and then you multiply it by 2r. That's the factor there. In the case of the sphere, you need a little bit of Pythagoras theorem application so that you can work out the radius of the slice based upon the distance x. So you know the distance x, you know the radius of the sphere is 2r. So you just try to use the Pythagoras theorem to get the radius of the slice. And when you do that, I have given the result here. And you will now notice that when you combine the cone and the sphere, surprisingly or fortuitously, but it's actually something which was by design as far as Pythagoras was concerned. It's not something, the cancellation is not something fortuitous or particularly contrived, but rather something which he thought about and created. So he is able to cancel the term pi x squared 2r times t from the cone and leaves behind the other term in the sphere, which exactly matches that of the cylinder. You can think of it as the cylinder balancing the cone and the sphere combined, and this is really a very beautiful concept. And having now established this, the rest is follows rather easily, because you can replace the cylinder by now a point mass lying at a distance r, and since you now know the volume of the cylinder, you can balance the volume of the cylinder at a distance r from the fulcrum, and similarly you can combine the volumes of the cone and the sphere. The aim of the exercise was to discover the formula for the volume of the sphere, the volume of the cylinder, and that of the cone being already known to Archimedes and, let's say, to us when we are trying to solve this problem. So the aim of the exercise was to obtain the volume of the sphere. It becomes the only unknown now when you replace all the geometrical objects by points located at the center of mass. And by this procedure, you can actually discover the formula for the volume of the sphere. So this is something really wonderful, and I think this is something which might be very appealing to all of us who are interested in the mathematics of these type of geometrical problems. So let's pass on now to how the conservation was done. So here you see in the first picture how the conservationist Abigail Quant, she had to cut open the binding. So after the binding was cut, the second picture on the right shows a side view of the binding itself. The white lines are the threads which are used in the binding, and it has been covered in glue. So it was very important that we do not destroy the part near the binding. It was possible now at this point to just make a cut and cut all the pages so as to remove the binding, but that would have destroyed the part of the book, part of all the pages which were close to the binding, which were actually the folds where the pages had been turned and folded. So there was a lot of writing which would have been in the folded region, and Abigail Quant did not want to destroy those material. The glue which you see had to be removed. The ancient glue is actually seen here, that's black in color. This was fairly easy to remove, and she could do it with an ultrasonic micro water spray standard method, and there was no problem in removing the black glue. The problem is that there was an unexpected layer of wood glue which you see in this picture, which is in white. This is something which must have been done in modern times. We don't know who did it to give the book some strength. A layer of glue, wood glue, was applied, and this glue is something which is very strong, and it's actually stronger than the parchment itself. So if you try to remove the glue, you also destroy the parchment. The only way would be to very meticulously sit down and scrape the glue very carefully with a scalpel, which would take a lot of time. But it was no mean task. In fact, it took her 4 years to get rid of this white glue. And, her patience paid out, because today we have recovered the book completely. And this would not have been possible if she didn't struggle for 4 years to remove this glue. The steps after are shown here. So this involved removing the wax. There was a lot of dirt. There was wax. The wax came because this was a prayer book, so it had been near candles, and so wax appears in different parts of the book. There was plenty of mold, and in fact, there was also glued paper on some of the pages, especially where the gold leaf forging was done. On these forgeries, on those pages, in order to give some strength to the paper, there was an application of additional glued paper. So these had to be removed as well. And you can see her work in the second picture on the right, where she is carefully unfolding the fragments. She has kept a record of each and every fragment. They were all photographed and recorded. As far as possible, she has unfolded the fragments to reveal the writing underneath it. In cases where the fragment has completely fallen apart, the fragments have also been kept and preserved. So a great deal of effort has been put in order to get the book in working order. So if you look at very carefully at the diagram on the right, you'll notice that there is faint writing underneath the main writing, which runs from left to right in this picture, because the picture itself is turned, the book is turned in the picture. So the main writing, which is dark in color, the text runs from the bottom of the screen to the upper part of the screen. I'm talking about the lower right, the picture on the lower right. So underneath it, you can see the text, which is the original Archimedes text, which is very faint. And the part which she's trying to straighten obviously has got very important parts of the writing in it. And this is the part where she wanted to keep everything properly recorded, and where the gum would have been. So the gum has been scraped off, and now the pages are being put into proper shape. The As each two pages, each double page is restored or conserved, you see the result of it on the last diagram, which is at the bottom of this slide here. You see it encased in a transparent cover. So this she did for all the pages, as in when the pages got complete, they were encased in a transparent cover, and in this form you can now actually see it in the museum. So this is how the book stands as of today. The next part of it is to reveal. So the restoration of the text starts now. So 1998 right up to 2016. In fact, even till today, people are doing research on this kind of work. The restoration really was done and completed by 2016. It involved various techniques which I have listed here, and which I talk about in the next few slides to give you an idea of how they are done. And finally, for each of the restoration steps, you have all the pictures completely available. It's an open access on web pages. There is also Google Books, which give you the final uncovered text. Let's look at the different techniques used. The liquid crystal tunable filter. This is a method which was used in the period of 2001 to 2006. So in the middle is the camera itself. The lower part of the camera, you see the lens, and finally after the lens is the liquid crystal tunable filter. This is a filter by which you can change the wavelength of the light which will reach the lens. The illumination with standard white light, and the camera is covered by a filter. The wavelength of the filter can be tuned by adjusting the liquid crystal. So in this way, the pictures of the pages could be taken at different wavelengths, that means different colors. When you do this, you could actually do what earlier 6 years work had been done by earlier people in trying to transcribe the text and make better pictures. In just 3 weeks, this team of people whose pictures you see here, they worked on this by this liquid crystal tunable filter, and they took photographs of all the pages in different wavelengths. They used a camera which was 600 dpi, a little bit modest by today's standards, and they used computer image enhancement, and in the end they produced pictures of all the pages. To give you an idea of what multispectral imaging looks like in modern days, like it's changed and evolved, and in fact this team also then went on to do it by this more modern method later on. So the initial work was done using a tunable filter, liquid crystal tunable filter. But today, this is not the way that you would record a multispectral image. What you would do is you would use fairly low illumination using LEDs. The LEDs are tunable. So now you are not making a filter on the lens. You are going to use just a monochrome camera. So this team could use a monochrome 50 megapixel digital camera. By now, the technologies were advancing, digital cameras became available, and resolutions were going up. So you could have really sharp pictures. The nature and quality of the computer software had increased tremendously, so images could be improved. But I think the key fact is that if you don't use a filter on the camera and illuminate in white light, but instead you illuminate it in wavelength which you are interested in. So this could be done by using LEDs, and the LEDs could be set to give their light in different wavelength regions, right from ultraviolet to infrared. So the pictures were taken from ultraviolet right up to infrared, and I've given some pictures here. On the left is the light source. It's covered in a way that you see on the second panel on the top right. The camera is shown in the bottom left side of the screen, and how the software looks like is shown below that, to the right of that. See how it works out. So here is a multispectral image, not of this palimpsest, Archimedes palimpsest, but of some other document. This is a mid-century, mid-5th century document, and I have shown you the visible light picture, which is on the left. So this is how the fragment of paper which you see on the left side looks like. It's also a palimpsest. There's writing underneath, which is at 90 degrees with respect to the text, which is in dark color. So the original picture on the left, you cannot read easily the writing which is buried below. We now take a picture of it using multispectral imaging, and this gives rise to different colors. So the red has become enhanced. The picture, the writing which is below, which was hidden, appears in red, and it is now standing out. So you now have a situation where you are able to much more easily read the writing which is below. However, the technique which is really much better than any of these methods which the team discovered, as far as the scholars were concerned, they weren't too happy with the first method of making images using the multispectral technique, but they preferred these images which you see here. So here what we do in ultraviolet fluorescence imaging is that the parchment is illuminated by ultraviolet light, say 365 nanometers. The ultraviolet light actually causes fluorescence within the parchment. That means the atoms in the of the parchment, or rather the ink in the parchment, they get excited, and when they de-excite, they emit light. We keep only the blue part of the light which is emitted. So you have ultraviolet light coming in onto the parchment, then it's scattered, and then you have a blue filter, so that we keep only the blue, and the camera sensor is then going to see. Now you can use a monochromatic camera. The camera is just going to see only the blue light, which is coming from the ultraviolet fluorescence. This is pictures which are, again, an example I give here, not from the original palimpsest, but another example just to illustrate how it works. So this on the left is a 5th century Arabic document, and on the right you see its ultraviolet imaging result. There is an illustration of a herb which is buried in the text on the left side, so not visible except to a trained eye. However, when you take the ultraviolet image, then you can see that herb picture very clearly in the picture on the right. So this is one of the techniques, ultraviolet imaging, which was worked quite well as far as the scholars were concerned. They worked with these ultraviolet images. This forms the major part of the scholars' work in transcribing the text. However, there remained a problem on these 4 pages on which the forger had worked and prepared gold leaf pictures, holy pictures. So I show you an example here. So in this example, from the palimpsest, you have a page on which a gold leaf portrait has been prepared, has been constructed on top, and as you see from the picture on the left. Now, when this is subjected to ultraviolet fluorescence and the pseudo-color method, the pseudo-color method, by the way, is a kind of an algorithm. It's a method by which we combine the original image with the ultraviolet fluorescence image and produce colors which are not the real colors, so we call them pseudo-colors. The text which has reappeared is red. But you can see that in areas where the gold leaf is obstructing, we are unable to unearth the real text easily. It's possible to work on these images for the scholars, but rather difficult. Much of the text would be missing and very difficult to reconstruct. So at this stage, this was the situation when some other method was to be thought of. Method which then was applied, which appeals to me because I'm basically an accelerator physicist and I have been working in my career in the Baba Atomic Research Center using the Pelletron accelerator located at TIFR for a major part of my career. So this part is appealing to me. It uses the Stanford Linear Accelerator, and at the Stanford Linear Accelerator in the US, there is a synchrotron radiation light source, which is one of the strongest light sources available in the world. So this light lab, this is the place where one can really have a chance to consider the best possible imaging which could be tried out. I show you the setup first. It's on the left side. On the left side, you have you can see the X-ray beam, which is coming from Hutch 6.2, and it's collimated through a 50 micron pinhole. It then illuminates these X-rays, illuminate the page of the palimpsest book, which is the black line which is inclined at an angle of 45 degrees. And there was a raster scan applied. So there is a stepper motor and it's doing the raster scan, which whose explanation is or whose details are shown in the second panel on the right. This shows you how you had a continuous scan in the X direction and steps in the Z direction. This whole thing is computer controlled, so you can finish the entire imaging. I think it took some 30 hours or something of beam time at SLAC. So the imaging is done after computer control. The detectors used, there are 2 detectors. I'll come to why 2 detectors in a moment. So they used, on the top you have this Canberra 13 element detector, and at the bottom you find the radiant vortex silicon drift detector. So 2 detectors are used, and then the beam is, the X-ray beam is monitored using an ion chamber, which you see on the right. The fluorescence, of course, for those of you who know it well, it's basically the iron content of the ink. So the erased writing, the original writing, contains iron. whereas the writing on which the prayer text was done, that does not. It is made with the conventional ink which has dye. So we are interested to make a fluorescence of the iron, and this could be done if you use an X-ray beam whose energy is slightly above, somewhat above that of the 1s electron in iron. So on the right panel, I have shown you what an iron atom looks like. The 1s electron, which is the innermost orbit, has an energy of 7.1 keV. So we use X-rays which are sufficient above the threshold for exciting these, for knocking out these electrons. And when you knock out this electron, then you get fluorescence. So the other electrons, they fall into this level, and that produces the fluorescence light, which we then detect using these two detectors, and the Canberra 13 element and the radiant vortex, which are above and below the parchment. So this here picture shows how an X-ray fluorescence mounting has been done, and in the center is the parchment, very well, nicely mounted. It's in a frame which will be moving with the XY stepper motors. The X-ray fluorescence was wonderful. It gave iron detection without any problems at all. The gold leaf therefore became completely uncovered. It had no problem at all in this method, because the X-rays, they go right through, and then it's iron that we are causing the fluorescence. We are tuned to that, so we don't have any interference from gold. But then what you see is that you actually see four layers of text, because you have now both sides of the paper. So you have, first layer is the prayer writing, the next layer is the actual writing on the of Archimedes, and then you go to the other side of the page from where you next get the image from Archimedes writing, as well as the last layer is again a prayer writing. So you get four layers of text in the X-ray fluorescence images, and not just two layers, which would have been rather nice, but that's not the case, because the X-rays, obviously, they penetrate and cause fluorescence on both sides of the paper. So to separate out the images from the two sides of the paper, that's why we used two detectors, one above and one below. And then by using a model to decide on the intensities which go up and down, the two sides could be separated. The images from the two sides could be separated out. The same pseudo color technique as before was applied, and the full text was revealed by the X-ray fluorescence method. So at last, the book decoding was complete. We had all the pages restored, including the 4 pages on which there were gold leaf paintings. So now I think by now you're curious to see what the final results look like. So from Wikipedia, I have taken the first picture. On the left, this is what the final images look like. To you, perhaps they may be still looking ugly and undecipherable, but no, that's not the case. For the scholars, there is sufficient information to decipher what's written on it. I have enlarged one paragraph for you on the right, and from my side, I have done a little bit of photoshopping. So I have inverted the image from black to white, and I have done some color replacements so as to give you the picture which you see, which is now fairly clean. So you may be wondering why this photoshops which I have done so simply is not applied to the original image which is published, and that's because the scholars are interested to see more than just what I show you here on the right. The picture here shows you how the scholars work. Let's take a fragment which you see, which is the top picture, which is having a blue background. If I Photoshop it, it will be looking like what you see below. So for a layperson, you might be interested in the lower picture and think that, oh, now it's readable. But for the scholars, they need to have more information, and that information would be lost if you try to Photoshop it further. So you see a message, this on the left, question to AQ. So they are asking Abigail Quant about the tear. So on the second line, in the middle of the second line, after the sigma, you see that there is a tear. They would like to know about the tear. Now, if we have photoshopped it and the tear is the picture of a tear is missing in my Photoshop, which is below, so they would not have got the information that there was a tear at that point. They have now asked a question: is the tear possibly original? Because Abdul Quant would know whether the tear was already in the original parchment, so that it was never written, nothing would have been written on that in the original text. However, if the tear has appeared later, then there is a missing piece of text in that area which the scholars would need to reinsert. So this is how the scholars work, and it's hard work. The scholars have transcribed the entire book, and it has become available to us all. So with this, I come to the end of my presentation. I thank you all for listening, and I thank you once again for your patience. Thank you very much.